Hey folks, I'm going to be going over with you the answers to the hypothesis testing worksheet. Before I do, make sure that you've read the handout, The Logic of Hypothesis Testing. So you want to have read through this before you even have started the worksheet. It's about 4 pages and I think will give you a good introduction to hypothesis testing. Okay, so let's look at our hypothesis testing worksheet. Looking at the A series, according to the null hypothesis, where on the number line is the population mean? Remember that the null hypothesis is like a treasure map. It tells us where we should be able to find the population mean. So here's our A series, and there's quite a few of these. 6 of them in total for sample sizes of 1, 5, 10, 25, 100, and also for 1,000. But for every single one of them, for the null hypothesis distribution, the mean is set to be 100. That is, the mean is thought to be a value of 100. Question number 2. Looking at the A series, for which sample size would you expect the best estimate of the population mean? And what was that estimate? Well, we'd expect the best estimate to come about when we have a really large sample size, and 1,000 is our largest sample size. And in that case, the sample mean was 99.42, so that would be our best estimate for where the true population mean is at. It's at 99.42 is our best estimate. Question 3. For each of the A series, write down the sample size and the standard error. As sample size increases, what happens to standard error? What formula specifies this relationship? So when looking at the handout here, you'll notice that it states what is our standard error for a sample size of 1. Standard deviation, standard error the same. In this case, it's 16. For a sample size of 5, you'll notice that standard error is smaller, 7.16. Then it goes down to 5.06 for a sample size of 10. For a sample size of 25, it's down to 3.2. For a sample size of 100, it's at 1.6. And for a sample size of 1,000, the standard error is 0.51. So one of the things you'll notice is that as the sample size increased, the standard error was decreasing. So we have, with the sample size increasing, the standard error is decreasing. The standard error is equal to the standard deviation divided by the square root of the sample size. So we got this value here, this 5.06, by saying 16 divided by the square root of 10. We got the 0.51 when we said 16 divided by a square root of 1,000. So as we increase our sample size, our sample mean should become a better and better estimate of the true population mean with less error involved, and we see that the amount of error is decreasing rather dramatically. Number 4, based on the hypothesis testing, the important comparison is between the empirical data and what? It's between the empirical data and the null hypothesis. The null hypothesis is like that treasure map. It tells you where you should be able to find the true population mean, and then we look at the empirical data, the sample mean from our results. And those two should be close together. They should agree. And if they do, we'll retain the null hypothesis. And if there is a significantly large enough difference, then we would reject the null hypothesis in favor of the alternative hypothesis. Number 5, we know that even if the prediction of the null hypothesis about the location of the population mean is correct, still, we expect some error between it and the empirical data. Why is that? Sampling error means that rather than getting the exact population mean every time, there will be variability in our results. Sometimes more, sometimes less than the population mean. It is even possible to end up with a non-representative sample due to sampling error. Right, so sometimes we may get a sample mean that's far away from where the null hypothesis says it should be, and it's just because we happen to randomly sample a very unlikely sample mean that was out in the tails of the null distribution. Number 6, when we calculate a z-test, what does it tell us? Z-test tells us the number of standard errors between the population mean, as specified by the null hypothesis, and the sample mean. That's That's the job of the z-test. So if the z-test is 0, then our sample mean is right on top of the population mean. If the z-test is 1, then that means that the sample mean is 1 standard error above the mean. So z-test is kind of like a tape measure. It's where instead of measuring in feet, we measure in standard errors. So whatever number we get for the z-test, that's the number of standard errors we are away from the mean. Number 7, for a two-tailed test, how many standard errors must the sample mean be away from the population mean, as specified by the null hypothesis, before we consider it non-representative? And the answer is plus or minus 1.96. So if the sample mean is at least 1.96 or greater, then we would consider it non-representative. Or if the sample mean was at least negative 1.96 or less, then again we would say that the sample mean is not representative. It's too far away. Number 8. What percent of the time, when the null hypothesis is correct, will we nonetheless inadvertently end up rejecting it? 5% of the time. So 5% of the time, we'll get a sample mean that is beyond that 1.96 cutoff value, that z critical value. Number 9. What percent of the time, when the null hypothesis is correct, will we end up correctly retaining it? So 95% of the time, we'll get a sample mean that's within plus or minus 1.96, and 5% of the time we'll get a sample mean that is at least 1.96 or greater, or negative 1.96 or less. Number 10, for the A series, did we ever make a type 1 error? Assume the null is true. So looking at the A series, did we ever inadvertently reject the null hypothesis? So to do that, we take a look at this drawing here. Here's our sample mean of 98.5, and you can see that it did not end up in the reject zone. So we retain the null hypothesis here, and our z-test was a negative 0.09, so that's pretty close to 0. It's pretty close to the population mean as specified by the null. Our p-value is really big, p of 0.925. Largest it could be would be a 1. So yeah, all this is going to be a null hypothesis in this case that we retain. For a sample size of 5, again, our sample mean is not in the reject zone. The z-test is 1.19. That's certainly not at 1.96. Our probability is 0.232. It's not 0.05 or less. So by all three of those criteria, we're going to retain the null. So that would be a correct decision. No error there. For a sample size of 10, again, our sample mean is not in the reject zone on either side. Our z-test didn't make it to the plus or the minus 1.96. Our p-value is greater than 0.05. So again, based on any one of those three criteria, we'd retain the null hypothesis. For a sample size of 25, again, sample mean isn't in the reject zone. Z-test is not greater than plus or minus the 1.96, and the p-value is greater than 0.05. So again, retaining it. By the way, if we'd reject the null hypothesis for any one of those three criteria, we'd reject it for all of them. So the three criteria again are: the sample mean is not in the reject zone, the z-test did not get into the reject zone, it wasn't greater than positive 1.96 or less than negative 1.96, and our p-value was greater than 0.05, so we again retain the null. And for sample size of 1,000, where we have the greatest accuracy, again, sample mean is not in the reject zone. Our z-test did not get beyond plus or minus 1.96, and the p-value did not become 0.05 or less. So no, we did not reject the null for any of the A series there. So for the A series, did we ever make a type 1 error? No, we didn't. If we assume the null hypothesis to be true, in every single case, we correctly retained it. No errors were made. Number 11, for A10, if the sample mean had been 112, would we have retained or rejected the null hypothesis? And we say rejected the null. So taking a look at A10, let's go over here. And again, it was if it had been 112. So looking at this here, 112. 112 would have put us into the reject zone. Our boundary conditions for sample mean are 90.08 to 109.92, and 112 would be beyond that. By the way, we got the 90.08 and the 109.92 by just taking that 1.96 and multiplying it by our standard error. So 1.96 times 5.06 got us the 9.92. Add that to 100 and you get 109.92. Subtract it from 100 you get 90.08. And again, we didn't get into the extreme zone with a sample mean of 104.65, but for a sample mean of 112 we would be able to reject the null in that case. Alright, for A5, if the sample mean had been 112, would we have retained or rejected the null hypothesis? So looking at for a sample size of 5, if it had been 112, well, it had to be beyond 114.32 for us to reject it. That's where this reject zone starts. So 112, we would retain the null hypothesis. It wouldn't be in that reject zone. So coming back, number 13. If your answers differ between 11 and 12, then explain what changed between A5 and A10. Why would that matter? So we have, with a larger sample size, the standard error became smaller for A10. With a smaller standard error, the difference between the sample mean and the population mean, as specified by the null hypothesis, became a bigger deal. All right, so as your standard error gets smaller, notice that the reject zone gets closer to 100. And by the time you get to A1000, the reject zone is starting there at 101.02 on this side and 98.98 on the other side. So as our sample size increases, our reject zone gets closer and closer to the population mean as specified by the null. So it's easier to reject it. Number 14. For any of the A series, if the p-value had been 0.06, would we have retained or rejected the null hypothesis? And the answer is we would have retained it because our p-value would be greater than the alpha level of 0.05. If the p-value had been 0.05 or less for any in the A series or any of the problems that we'll be doing in our course, we'd reject the null. Okay, for which of the B series would we reject the null hypothesis? And it says B100 and B1000. So heading over to the B series, are we going to reject the null here? Oh, it's so very tempting. Look, the sample mean is pretty close to the reject zone. The z-test value, it's not 1.96, it's 1.91. The p-value is 0.057. All three of these measures are directly linked to one another. If we could have rejected null for any one of these three, we could reject it for all three. But sadly enough, this is just slightly too big. 0.057 is bigger than 0.05. 1.91 is just a little bit smaller than 1.96, right? And our sample mean didn't get in the reject zone, so we'd have to retain the null for sample size of 1. For a sample size of 5, it's pretty clear we're going to retain the null. Our sample mean is nowhere near the reject zone. Our z-test is pretty close to 0, indicating the sample mean is close to the population mean as specified by the null, and our p-value is way bigger than 0.05. For an n of 10, again, sample mean is not in the reject zone. Z-test didn't get to the negative 1.96, and our p-value didn't get to 0.05. Coming back up, let's see, right here, and going over. So for a sample size of 25, again, we're seeing that the sample mean is not in the reject zone. The z-test is still too close to where we would expect the population mean to be. The sample mean is only like half a standard error above the mean, and our p-value is way bigger than 0.05. Now for a sample size of 100, our sample mean is in the reject zone. Our z-test is 2.53, and that's because the sample mean is 1, 2.5 standard errors to the right of where the null hypothesis says that it should be. That's a pretty big discrepancy, a significantly big discrepancy between the null hypothesis and our empirical data of the sample mean. P-value, probability of getting something like this just due to sampling error is essentially 0. It's less than 0.05. We're going to reject the null hypothesis. It's really clear. By the way, normally we don't check all three of these criteria. I'm showing you all three just so you can see the connections between them. Typically, you might just do a z-test, and if the z-test came out larger than 1.96 or smaller than negative 1.96 for a two-tailed test, you'd reject the null. You wouldn't have to draw it or do the p-value. If you're using SPSS, then in that case, you may be given the p-value, and it's really nice to look and just say, oh, is it 0.05 or less? And SPSS or another statistical package will actually put a little asterisk next to a statistically significant result so that it draws your attention to it. Okay, for a sample size of 1,000, well, our sample mean is definitely in the reject zone. The z-test is 10.55, which says that our standard error is, it's just like 0.51, right? So we have a sample mean of 105.38 between where the null hypothesis says the population mean should be and our sample mean. That's 10.55 standard errors out there. It's way out there. P-value, you wouldn't get this due to sampling error very often. The probability is essentially 0. So coming back to it, from which of the B series would we reject the null hypothesis? For B100 and B1000. Number 16, if we're able to reject the null hypothesis, what does that mean regarding the alternative hypothesis? Well, if you reject the null, then you support the alternative hypothesis. In terms of our logic of hypothesis testing, we're basically seeing the duking out between the null hypothesis and the empirical data. Alternative hypothesis is kicking back over here on the side just watching the fight. If the null hypothesis gets taken out, then we're left with the alternative hypothesis, which is then supported. Okay, let's see. Number 17. If you retain the null hypothesis, is that the same as proving the null hypothesis true? And our answer is no. In a court of law, if we do not have enough evidence to convict a person of a crime, that is not the same thing as proving the person is innocent. We might have a sample mean that was almost but not quite different enough to reject the null. So we retain the null. One never proves anything using hypothesis testing. It's probabilistic. So we either retain the null or we reject the null. And when we reject the null, then we get to support our alternative hypothesis, also known as the research hypothesis. If you reject the null hypothesis, is that the same thing as proving the alternative hypothesis is true? And again, we say no, we cannot use the term prove. Do not use it. This is because with random sampling, there is always a possibility we end up with a non-representative sample. We can only say that we support the research hypothesis. Number 19. With the B series, we are doing a two-tailed test. For each of the B series, write out the absolute value of the z-test, ignore the sign, and the p-value. Order your results using the absolute value of the z-test from the smallest to the largest. Okay, so just briefly coming over here to our B series. Let me scroll it over. Here's our z-test. Here's the p-value, right? So we're going to ignore the signs. So this would be up here treated as a 1.91. And over here this would be treated as 0.06. That's what absolute value means. Ignore the sign, and that's the p-value. And when we write that out, we see that we go from a z-test of 0.06 all the way up to a z-test of 10.55. And as the z-test is getting bigger, look at the p-value, right? In other words, the z-test tells you how many standard errors is a sample mean from where the null hypothesis says it should be. And the p-value says if the null hypothesis is correct, what's the probability of getting that result due to sampling error? And as the z-test gets bigger, probability gets smaller, right? So we'll reject the null hypothesis if that z-test is bigger than 1.96 or the p-value is less than 0.05. Number 20, for the B series, we are doing a two-tailed test. What is the relationship between the absolute value of the z-test and the p-value? And our answer is, as the z-test increases, the p-value decreases. 21. Why do you think the relationship exists? As you move further away from the population mean, as measured with the z-test, there is a lower probability of getting a sample mean that far out. Most sample means are close to the population mean, and relatively few are far away from the sample mean. Okay. Yeah, so most of the sample means are going to be close to the population mean. Very few are going to end up being far away from where the population mean specifies that it should be. 22. For the B series, did we ever make a type 1 error if we were to assume the population mean of 105? Well, as it says here, this is a trick question. With the population mean truly at 105 instead of 100, as specified by the null hypothesis, then clearly the null hypothesis has to be false, right? The null hypothesis is at 100, and truly it's at 105. We would know we'd have to that the null hypothesis is incorrect. It is only possible to make a type 1 error when the null hypothesis is true. Question 23. For the B series, did we ever make a type 2 error, assuming a population mean of 105? Yes, for B1, B5, B10, and B25. We would have incorrectly retained the null hypothesis when we should have rejected it. So basically, if the true population mean was at 105, then ideally when we did this hypothesis testing, that should have been made clear and we should have rejected it. And we were really close to rejecting it when our sample size was 1, but it just wasn't extreme enough to do so. So in that case, we would have incorrectly retained it if indeed the true population had been at 105. Here we retained it, and again, if the true population mean was at 105, that was a mistake. That we should have rejected it, and that's going to be true also for sample size of 10 here, and also for a sample size of 25. In all those cases, we retained it. It was only when we got to sample size of 100 and 1000 did we have a large enough sample to see very clearly where the true population mean was likely to be, and in these cases we were able to reject the null. Okay, number 24. For B25, if the sample mean had been 89, would we have retained or rejected the null hypothesis? If it had been 89, our sample mean would have been here, and we would have ended up retaining the null hypothesis. The null hypothesis, no, correction there. If it had been 89, it would have been in the reject HO zone. So in that case, we would have rejected the null hypothesis. Okay, yeah, rejected the null hypothesis. Had the sample mean been 89, then the z-test would have ended up being greater than or equal to that negative 1.96. Additionally, had the sample mean been 89, the probability of the result occurring with the sampling error would have been less than or equal to 0.05. So yeah, so then our z-test would have been below the z-critical of negative 1.96, and we would have rejected the null. For B1000, this is number 25, why would we be willing to reject the null hypothesis if the sample mean had just been 101.2? Connect your response to a sample size. So basically, with the larger sample size, we have greater accuracy, and because we have greater accuracy, we would expect the sample mean to be closer to where the null hypothesis says it should be. And so at 101.2, that sample mean is in the reject zone. For a smaller sample size, there's much more variability, and so in that case, we wouldn't be able to have rejected the null hypothesis so easily. But larger sample size, greater accuracy, easier to reject the null hypothesis. Number 26, for any of the B series, if the p-value had been 0.04, would we have retained or rejected the null hypothesis? And the answer is, with our alpha level set to 0.05, we'll always reject the null hypothesis when our p-value is 0.05 or less. And in our course, we'll always have alpha set to 0.05, so as long as p-value is 0.05 or less, we reject it. Number 27, for the B series, why would we say that we are conducting a two-tailed test? And it says here we have two reject zones, one on each tail. This is also called a non-directional hypothesis. So with the B series, you got a reject zone on the left, reject zone on the right, covers both tails. It is two-tail. Number 28. For the BB series, why would we say we're conducting a one-tailed test? And we have a single reject zone, one on just one of the tails. This is also called a directional hypothesis. So for the BB zone series over here, you can see there's only one reject zone. It's just on one tail. You'll notice also that when we went from two-tail, where it's plus or minus 1.96, when we go to the one tail, if we expect it to be larger than what the null hypothesis specifies, it's plus 1.645. And so we're going to have that one-tailed test for each of our BB series, whereas if the Z test ever gets to be positive 1.645, then it ends up in this reject zone. And it's a 5% chance of that happening just due to sampling error that we'd reject the null there. Okay, coming back up. Number 29. Are there any in the BB series using a one-tail test where we reject the null but did not do so in the B series? That is when it was two-tail. So we have here, it's going to be the case for BB1. With the one-tail hypothesis test, our p-value ended up being 0.028, which is less than or equal to 0.05. With a p-value of 0.05 or less, we can reject the null. Additionally, our z-test is 1.91, which is greater than the z-critical of 1.645 needed to reject the null hypothesis. The null hypothesis could be rejected for either reason, either the z-test being greater than or equal to 1.645 or the p-value being less than or equal to 0.05. So let's take a look at that one. So here it is, and you can see a sample mean is inside the reject zone. The z-test is greater than that 1.645 value, and the p-value is less than 0.05. So all three things point to the fact that we can reject the null. And we weren't able to do that when we did it as a two-tailed test. It just wasn't extreme enough. So that's the benefit of the one-tailed test, you predict the correct direction, then the requirements are a little bit more relaxed, 1.645 instead of 1.96 standard errors away. Number 30, whether we do a one-tailed test or a two-tailed test, what is our alpha level? Alpha level is always set to 0.05. 31, if the alternative hypothesis is that people's IQ will be different than 100, will we do a one-tailed or two-tailed hypothesis test? And our answer is we'll do a two-tailed test based on the keyword difference being used. If we expect a difference, the result can either be greater than or less than that specified by the null hypothesis. A two-tailed test is also called a non-directional hypothesis. Number 32, if the alternative hypothesis is that people's IQ will be greater than 100, will we do a one-tailed or two-tailed hypothesis test? And our answer is we'll do a one-tailed test, given that the alternative hypothesis predicts its results to go in a specific direction. This is also called a directional test. 33. What is the advantage of the one-tailed test over the two-tailed test? And what is the disadvantage of one-tailed test? So for a one-tailed test, it does not require as extreme a sample mean compared to the population mean specified by the null hypothesis. For a one-tailed test, the sample mean need only be 1.645 standard errors away in the predicted direction. The disadvantage is that the actual results may go in the opposite predicted direction. Even if they go extremely in the opposite predicted direction, we couldn't reject the null since the one-tailed test only works if the results go in the predicted direction. 34. What is the advantage of the two-tailed test over the one-tailed test? What is the disadvantage of the two-tailed test? A two-tailed test will enable you to reject the null hypothesis if the results are at least 1.96 standard errors away from the predicted population mean in either direction, and that's the benefit. It could go either way. The drawback is that the results must be further away from the predicted mean when doing a two-tailed test than if we had done a one-tailed test. Two-tailed test, it's got to be 1.96 standard errors away. For a one-tailed test, as long as it's in the right direction, it only has to be 1.645 standard errors. Number 35. For a one-tailed test where the alternative hypothesis predicts performance greater than that specified by the null hypothesis, how many standard errors must the sample mean be away from the population mean before we consider it non-representative? It must be 1.645 standard errors away in the predicted direction. By the way, we get that 1.645 because if you look it up in the z table, it'll tell you that the proportion of the distribution beyond that, so z and beyond, is 0.05. So that's the cutoff for a 0.05 proportion or probability. 36. Assuming for the moment that the null hypothesis is true, what percent of the time, when using a one-tailed test, will we nonetheless inadvertently end up rejecting it? 0.05, right? Because our alpha level is always set to 0.05, so there's always a 0.05 chance that we might incorrectly reject the null hypothesis when it's true. What is our alpha level for all the scenarios? As mentioned, it's always set to 0.05. That's kind of like our industry standard. 38. For a one-tailed test where the alternative hypothesis predicts performance to be greater than what is stated in the null hypothesis, if the z-test is 1.70, would we retain or reject the null? And our answer is we would reject the null, since a positive z-test is predicted that is equal to 1.645 or greater. So as long as it's 1.645 or greater, you get to reject it. And it's a positive 1.645 because we were predicting the results to be greater than what the null hypothesis said it should be. 39. For a one-tailed test where the alternative hypothesis predicts performance to be greater than what is stated in the null, if the z-test is negative 1.70, would we retain or reject the null? So let's restate this and say for a one-tailed test where the alternative hypothesis predicts performance to be less than what is stated by the null hypothesis, if the z-test is negative 1.7, would retain or reject? Well, if the results had gone in the predicted direction, then that would be a good indicator we might be able to reject the null. But again, what does this actually say? It says, what if it had predicted the results to be greater? Well, if it predicts the results to be greater and the actual results were less than, you're out of luck. That's a drawback to that one-tailed test, is if your alternative hypothesis says better than and the results are worse than, doesn't matter how worse, you're going to end up retaining the null. So we retain the null since the positive z-test is predicted that it's equal to 1.645 or greater, and the z-test was negative, so it's smaller than the 1.645. If we predicted the results to be less than the stated null hypothesis, then we would have been okay, as we'd then expect a z-test of negative 1.645 or less, which would be true for if the z-test had been negative 1.70. Number 40, for BB25, if the sample mean had been 50, would we reject or retain the null, and why? Okay, so if the sample mean had been 50, that would have been way out there on the left-hand side, right? Super extreme. The negative z-test would have been a really large negative number, but it would have been going in the opposite direction of what was predicted. Our reject zone's over here. So since the sample mean would not end up in this reject zone, we'd have to retain the null no matter how extreme it is. By the way, I show this reject zone as a rectangle, but no matter how far out the sample mean is to the right, imagine that it would be enclosed by this reject zone. It doesn't necessarily just stop here. It continues on to the right. 41. For BB100, if the sample mean had been 105, would we reject or retain the null, and why? So looking at BB100, if it had been 105, then we would get to reject the null for BB100. Let's see what it says. We would reject the null as the z-test would be greater than the critical value of 1.645. Yeah. 42, for BB1000, if the z-test had instead been a negative 1.97, we would reject the null. or retain it, and why. And well, remember for this BB series, it's all a single or a one-tailed test, all saying that the sample mean should be greater than the what the null hypothesis specifies the population mean being. So we're going to only reject the null if our sample mean is greater than, by a significant amount, 100. So this question said, what if the z-test had been a negative 1.97? That would have meant that the sample mean was below, and there's no reject zone below. When you do a one-tailed test, you specify the direction, and if the results don't go in that direction, you're out of luck, and if they do, well, then it's easier to reject. Number 43. For each of the BB series, we are doing a one-tailed hypothesis test. Write the z-test value and the p-value. Order your results using the z-test value. Start with the negative 1.69 and end up with the 10.55. So we get our z-test value from here on the left, and we get the p-value from here on the right for each of our scenarios. And you can see that as the z-test value gets bigger, the p-value gets smaller. And in this case, since it was a one tail, the z-test had to be at least 1.645 or larger. And so that's the case for z-test of 1.91. And our p-value, likewise, would have to be 0.05 or smaller. And so that would also be true. If either one of those is true, you're good to go. 44. For the one-tailed test, what is the relationship between the z-test and the p-value? As the z-test value increases, the p-value decreases. And 45, fill in the table below. If the null is true and you choose to retain the null, that was a correct decision. If the null is true and you reject the null, that was a type 1 error. If the null is false and retain the null, that was a type 2 error. And if the null is false and you chose to reject the null, that was a correct decision. All right, I hope that this worksheet and going over the answers was helpful. And if you have any comments or such, please reach out to me. Take care.